Hello. Hello. Yeah, the sound is probably I need to put it here. It's been a while as usual. And I will write a contest 24th round 947. Okay, maybe we can also open all these and no, it is called team reference. Yeah. Good. So we also have today a lot of duels. Really a lot of duels. I called a lot of people here. Well, some of them possibly will not participate. For example, I suppose ISAF27 maybe will ignore this round. But still, there are a lot of duels today, even if many of them refuse. Of course, this is the most important duel today. But we'll see. I forgot to call Budalnik. Okay, I will call him right now. Okay, he is called now. Here we also can see Pashka and 300 IQ. Okay, I think we will see if he participates during the round. Oh no, he's writing. Okay. Budalnik accepts. So now we are ready to start. Let's go. Let's go. Let's go. Okay, and everything's lagging right now. We can see the problems. Bazooka and the Mokas array. Could become sorted in non-decreasing order after performing the following operation. Split the array into two parts and swap. Ah, of course it is just some cyclic shift. Yeah, so it's kinda easy. We need to read the array. We need to repeat it twice. And we need to check whether there are n elements in non-decreasing order after this operation. Yeah, and we can do it like so. Let's go for int I is CR is 1. So what do we do here? So if a bi is at least bi minus 1, we say plus plus cr, else cr is 1. And after that we say that emit is max of mx and cr. Well, that's basically it. Now we need to compile it, and we need to check it on the examples. No, what's wrong? Ah, yeah. So now we see no yes, yes. And I can submit it. Okay, problem B. Okay. A is beautiful and there exist two numbers I and j such that for all k, ak is divisible by either ai or aj. So we can divide the array into two parts. Okay, so let's take the minimum element in here. So let's take the minimum element ak. So definitely it should be divisible by either ai or aj. So it should be one of them. So we always take the minimum element and the minimum which is not divisible by this minimum. So what do we... Ah, we again we need to say yes or no. This is nice. Okay, so what do we do? So we start with minimum element of A. Now we take, so if if I is not divisible by the minimum element, we say that Smn is minimum of Smn and I. Yes? Okay, now we need to check that each element is divisible by either Mn or Smn. Great. So let's check that again. No, yes, yes, no. What? Let's try again. Okay, we submit it. So I would like to recheck it, but I am just speedrunning, so probably it's not the case. I'm probably not going to recheck it again. So chum and mockus array. Yeah. Choose some indices L and R, take the median, and set all values to be equal to this median. What is median? Median is m plus 1 over truth element. M plus 1 over truth over second. So why? Ah, makes sense. Makes total sense. What is the maximum possible value of this number? So we want to maximize this number. Okay, we can only take two element arrays and each... Ah, no, we cannot. We cannot take only two element arrays. Okay, let's take the maximum. It seems that we cannot always... We cannot make any number bigger than the second maximum. So I kind of think that it is just the second maximum of this array. Yes? It's just the second maximum of the array. Yes? Yeah, I think so. So now we have infants. And here we need to return nth element. Is nth element void? I don't. Oh yeah, it's void. So a begin, a end -2, a end. Okay, and we return a dot r begin first. Yes. Let's try this. 1 4. So again, let's understand it somehow. So you definitely cannot make it bigger than the second maximum, but if you have the second maximum, you can just always take maximum, second maximum, and any number. Yeah, it should be easy this way. Ah, sorry, no, this is stupid, because we need to take the median of subarray. No, this is this is stupid. No, we should not submit it. What about subarray? So I need to take on the subsegments. Is it correct this time? So if I had... Okay, so let's take all two elements, two element pairs. Oh, and let's take the biggest minimum. So if I have two consecutive numbers which are at least a, I can make the whole array at least a. It is simple. I just do like this and then like this. So if I have two elements at least a, then I can win. So what if I don't have two elements, consecutive elements which are at least a? Can I take... What if I have three elements which are such that... Okay, I can take three elements. So the question is, do I just need to take the biggest median among three element subarrays? Do I just need to take the biggest median among three element subarrays? Probably. But why? Can I make it bigger than this? For example, I have 10 to the power 9, 10 to the power 9, and here I have like 1, 2, 3. Does it necessarily mean that I cannot make it bigger? Okay, let's say that A is the maximum median of such subarray of size 3. Can I make any number at least A, bigger than A? So is there a subarray in which there is the median is bigger than A? Probably not. Probably not, because why? Okay, let's divide by in groups of 3, and in each of them the median is at most A. And if in total it is at most A, okay, the problem is that the last element can be greater. So if there are 3 elements, then they're definitely at most A. If there are 2 elements, then also it is at most A, just because if I add any one more element, then it becomes greater. The problem is it can be greater than A. For example, 10 to the power 9, then something, then something, then 10 to the power 9. Okay, probably yes. Probably yes. I think so. Yeah, I think so. So let's do it somehow. So Sierra. Okay, something like this probably. Okay. Okay, I think that it should work. Although I don't know. But definitely people are solving this problem. Yeah, let's try this. Okay, let's try this. I feel like it should work. Yeah, it's fine. I think I'll have hard time proving it during the tutorial stage. Or maybe someone hacks me. So we have a tree with n vertices. Initially they are all white. We have two chess pieces, which are initially located on vertices A and B, and in one step we move A to a neighboring vertex, and if the target vertex is white, then this vertex So for us, the best situation is if they both are in same vertex, because we can move the piece A somewhere and immediately move B to the same point, to the same place. So the vertex is colored blue. However, we cannot. So I don't know. So what can I do? What can I do? I have a tree. Yeah, I have some tree. I have some vertex A, I have some vertex B. So if I make the full Euler tour for this graph, it is of size 2n minus 1. However, if I take the farthest point from this vertex, yeah, for example, this is distance d, I can subtract d. So this is how much it takes to color all tree red. What can I do with this vertex? I simply can move it here and then color everything. So I can spend additional like b minus distance AB time to move B here and then color everything. So probably the answer is this formula. And if A coincides with B, it's easily the case. However, maybe we can do it faster. Yeah, for example, let's look at this picture. So A is here, B is here, and we have a bamboo. Then A moves here, B moves for what seems to be a correct solution. B moves here, then they meet in some point. Then B goes here, and then B goes back. So in total, it seems like A should go all these n-1 edges, and then B goes back n-1 more edges. So in total, it seems like the answer is 2n-1. But here we have the answer n-1 plus 2n-1 minus n-1, which is also 2n-1. I don't know. So I have a good hypothesis, but maybe it's wrong. Maybe I just need to take 2n-1, add the distance between A and B, but subtract the distance between A and the farthest point. I don't know. I don't know. Probably my hypothesis is correct because we just see a lot of people solving problem D. Do we? Yes, and we don't see a lot of people who fail this problem. So probably I'm right. Probably I'm right. So we read T, we read N, A, and B. We subtract 1 from A and B. And now we need to read a tree. Oh, okay, and we need to put here VAB. VAB. Okay. Let's go. So here we have VAB. What do we do? I always forget what it does. What does it do? No, this does it. No, it's actually fine. Yeah, it's actually fine. Okay. So we do this. Now we go through. So we need to find the farthest point from. So okay, let's make vi dist. Take once n equals fitted size plus 1. Here we put n, dist n. Then we call dfs from point A Actually, it feels suspicious that we need to go. Okay, I probably have a counterexample. So let's again take a bamboo, but this time B is here and A is here. So it feels like we need to go from A to this vertex, and then we together go to the right. So the answer is distance from AB plus n minus 1. Okay? And here the answer is the same. Okay, what about A being here? Okay, I don't know. Let's continue. So we call DFS AG minus 1. Probably distance of A is 0. We call DFS. And then we need to take n minus 1 times 2 plus distance B minus max element of distance. Okay, so here we need to say that we go through all neighbors of V, and if distance of 2 is minus 1, then we say that distance of 2 is distance of V plus 1, and we call DFS for 2G distance. That's probably it. And we are expecting 2, 8, 13. No, it's 14 this time. Why? Okay, we have a tree, which we can take a look at. 5, 4, 7, 1, 5. 1, 8, 3. 7, 2, 8, 6, 3, 4. 3, 4. Ah, because 5, 4 is not an edge, is it? Yeah, 5, 4 is not an edge. 3, 4 is an edge. Yes. So this is our vertex A, this is our vertex B. So I expected the answer to be like 2n minus 1 plus the distance between A and B, which is 4, and this is like 8, and minus 4 again, so it is 14. However, we can do it in 13 moves somehow. Ah, we can go here in 4 moves. What? We can go here in 4 moves? And then we can finish the traverse. So we go here, 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 here. So 1, 2, 3, 4. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, probably what we really need to do is we need to meet with these two vertices, and only then we do something. Okay, so if the distance between A and B is even, then probably we take the vertex in the midpoint between them. We probably take the vertex in the midpoint between them, and then we just make this formula 2n minus 1 minus the farthest point from this point. Okay. Okay. So what if the distance is odd? For example, there is one edge between them. Also, there is kind of a problem with... Oh my god. So actually, the initial vertex is not colored automatically. So for example, if we are here, so if we are in a bamboo and we are here, actually we need to go here, then go back, and only then we go here. Which is creepy, to say the least. Okay, so if the distance is even and it is R and B are in different points. Initially the vertex A is painted red, and if A equals B, the vertex A is painted blue instead. Okay, fine. Then it's fine. Then it's comfortable to solve this problem. Okay, what if then the distance is odd? So initially, so this is red and this is blue. Then we just take this point, I think. Yeah, we just take this point, but in the end we will have to add 1 to the answer. Okay. Okay, probably it makes sense, although I don't like it a lot. So, let's see. Let's see. So this DFS is fine. So also I want to store parents. So here we say that P parent of 2 is V. Yes. So what do we do? First of all, we need to find the distance between A and B. Then we need to find the vertex in the middle between A and B. To do that, we need to take M equals B, and then for these many steps, say that M is parent of M. Okay. So now we have found the middle point. Int answer. So int answer is actually what? So this is this number. Then we need to just subtract. We calculate how much time we needed for B to go into this point M. Yeah, so this number. And then we need to subtract the distance between M and the farthest point. Okay, to do that, we also need vi md n minus 1, mp n minus 1. We need to say that this m distance of M is 0. Call this function for M. Yes, probably that's it. Okay. I don't like that at all, because I shouldn't have again submitted this so fast. Yeah, this is actually good. What's the error? Okay, probably I cannot read it like this for some reason. So actually I want some test, probably. Let's look at some bamboo or not. Okay, I want to look at some bamboo. For example, if I have 6 vertices, 1, 6. So what do you do in this case? Probably yes. This is the again a compilation error. No, it's not. You see how slow I am? What is that? Why do I have such a bad place here? Okay, now it's a bit better, but still it's sad, to say the least. Thematics, maybe. Maybe there is some math. Maybe I don't want to solve it. What about my friends? Okay, we're kinda in a garbage position. Okay, probably we need to solve this problem now. Define the binary encoding of a finite set as f of t. So we're given an integer n along with 2n minus 1 sets, 2 to the power n minus 1 sets. We need to find all sets S that satisfy the following constraint. S are here, it can be empty. For all non-empty subsets T here, what? Ah, the size of S intersect T is here? What's happening? So again, we're given several sets. We're given several sets. For each non-empty subset T, we want V f of T to contain the size of S intersect T. Ah, so just for all non-empty subsets T, we know the sizes of intersections which are allowed. We just know the sizes of intersections which are allowed. Okay, let's start with something easy. For example, let's take T consisting of one element. Then S intersect T is of size 0 or 1. So if both 0 and 1 are allowed, then we're happy. However, they can be not allowed. Hmm. Yeah, let's try something like this. Let's iterate over all elements. And for each element, we say that the difference between S intersect T with this element and S intersect T without this element are at most 1. Ah. Well, it's a strange problem. I don't know what to do. Chain queries. We are given a tree of n vertices. We are asked to perform Q queries. Toggle the color of vertex U. After each query, you should answer whether all the black vertices form a chain. That is, there exist two black vertices such that the simple path between them passes through all the black vertices and only the black vertices. Wait. Oh, if it is a HLD problem, I don't want to solve it because I haven't written an HLD in several years, to say the least. Okay, so first of all, I can store the number of black vertices. This is easy. And also I want to store... if I know the number of black vertices and the sum of distances, for example, between the black vertices, this would be nice, actually. This would be nice? This would be nice. If I knew the number of black vertices... Okay, so... I want two things. I want the number of black vertices and the sum of distances between two black vertices, between all pairs of black vertices. So I want these two things. And if I do it, I can solve this problem. Okay, in order to do that, why is that? Because this is actually... No, it's actually not working. It is actually not working. No, it's actually bad. I cannot do it. So I have some rooted tree. So all vertices look like this. Some path like this, and then some path like this. So I can probably store the LCA of these vertices. Yeah. I can probably store the LCA of these vertices because simply I can store... not the LCA, but the top vertex. So I can store the top vertex of this path with something like a multiset. So I know this vertex and I want to find... Also, I can store, for example, this vertex easily because this is the lowest vertex. So I can store the top vertex and the lowest vertex. Okay, I can check that. Okay, never mind. Never mind. Okay, for each vertex, I can store the number of its children, which are also black. Yeah, it's easy. Just when I take a vertex, I add 1 to its parent or subtract 1 from its parent. So for each vertex, I know the number of its black children. Yeah, so what do I need to store? For each vertex, I know the number of its black children. Yes? Yes. So therefore, I can store the number of vertices for which their parent is also black. The number of black vertices of which the parent is also black. This is easier. When I add a vertex, black vertex, firstly I check that its parent is already black and maybe add 1. And if its children, it has some black children, I add the number of that black children. And vice versa if I make it from black to white. Okay. So I know the number of such edges, the number of vertices who have a white, who have a number of black vertices who have black parent. Okay, so here the number of black vertices with black parent should be like b minus 1. But this is not enough because I can have something like this. I can have a tree, which is also fine. But I also want to calculate the number of vertices. Okay, first of all, it can only be connected. So I only need to check if, for example, I can check if I have only one or exactly two such vertices. So black vertex without black children. Can I calculate the number of black vertices without black children? Probably yes. Yeah, again, so when I add a black vertex, if this is also black, then I subtract 1 from the number of black vertices without black children. And if it does not have black children, then I add 1. Okay, let's try this. Problem is like technical, but okay. So what do I have? I have N and Q. N and Q. The initial colors of vertices then. Let's call it C. C. Is it B? 1. Then the tree. V. Also I need Q. Q is Q, so VI Q. Okay, so V VCU. Well, and the answer is vector booleans. Great. Great. So what do I want? I want for each vertex, I want its... For each vertex, I just want its parent. So let's somehow find all parents. Yes, so VIP size n. IP of size n. Then I say that then I call DFS of 0, for example, G and p. And I need to say here -1, but p0 is 0, and in the end p0 is -1. Also GCC lists from edge lists of v and n. Let's go. So first of all, I need to store all these c's. So let's say we have VPL of size n, which is initially right. So let's go. Let's go through C, and if CI, then toggle of I. So let's go. And so what do I also want to have? So first of all, API ans of size q. Okay, let's also say that toggle should return if it is a path. So answer I equals toggle of UI and return answer. Great. So let's do it. Let's do it. So we can definitely say that LX should equal not LX. What else do we do here? So first of all, let's calculate the number of black edges. Yes. So int addition. So if LX is true, then -1, else 1. So this is it true that, so if this is 1 if we added a black vertex, and -1 if we removed it. So if our parent is black, then the number of black edges is increased by addition. Right. What else do we need? We also need to store the number of vertices. We also need to have, for each vertex, we need to know the number of its black children. Black children of size n. So we always say that black children of px is increased by addition. This is always true. We also need to say something about our children. So first of all, we can say that the number of black edges is added addition times the number of our black children, so BC of x. And also the number of our black children did not change. So this is now working. Okay. So what next? Okay, now so we can just return. Is it true that the number of black edges is? Let's just also store the number of black vertices. BV is 0. So BV plus equals addition. So first of all, BV should be greater than 0. Also, the number of black edges should be equal to BV minus 1. Okay, what next? It is not enough because it still can be like a connected subtree. So we also want to know the number of vertices. We want to know the number of vertices which don't have any black children. So the number of vertices without black children should be at most 2. Black, so YBC is BVBC is black vertices without black children. So it should be at most 2. So let's think, what do we do? So there are 2 ways how we can change it. First of all, our cells. So if black children of X is 0, then we are a black vertex without black children. Black vertex without black children plus equals addition. So what about our parent? So probably our parent, for our parent something changed. So we can do it here. So if our parent is black, or if it is black, we can do it here. So if the number of black children of our parent is 0, then we subtract 1 from this. And now we do it again. So if now it is 0, then we increase it. Okay, so I hope I did not fail to do it correctly. Unfortunately failed to do it correctly. This happened because I was not accurate with it. So N and Q, then C of size N. We need to read it like this. Okay, probably we need to do it like this. No, we cannot read it. Okay, so great. Still no, what's wrong with you? Unresolved externals. Ah. I'm feeling dead inside. No, no, yes, yes, no. Probably, yes. Yes, 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 yes. Ah, this is bad. This is not good, yeah. So let's see. So we have everything initially black. What is the structure of the tree? 3, 5, 2, 5. 1, 5. 3, 5, 2, 5. And 3, 4. Good. So in this tree, everything is black initially. So when we toggle and we have 3 queries. Toggle 1, toggle 1, toggle 1. So when we toggle 1, it becomes a tree. Then we again toggle 1, and it's not a tree. It's not a path. So, yeah. We are kinda not understanding why it's happening. So, let's jump. Let's jump into our function. So, we need n equals 5. It's already 5. Yeah. So, addition is 1, yes. PV plus equals addition, so it's 5. LX is not LX, so now it's true. Then we go if px is not -1, which is if it is not a root, then we do something. Yeah. Ah. Yeah, I see. So actually it's a problem. So I thought that we have a path if we have exactly 2 vertices like this. However, it's not the case. We also don't want such a vertex. So a vertex. So if we have a vertex, what should be the easiest way to check it? Maybe I want to store the number of vertices with exactly 2. Maybe I can just store the number of vertices with degree at least 3, I think. So degree at least 3. No, I don't like it. I don't like it. I don't like it. So actually it's the only problem now, that I have a path plus something like this. I want to eliminate it. How could I do that? I think the problem should be here. So if a vertex, so I don't like it when I have. So okay, let's say that I ban a black edge, a BB edge, if here I have at least two children, black children. So if I have at least two black children here, then BB is banned. So I calculate the number of BB such that here I have at most one black child. Yeah, so what can happen? So I add a black vertex. Okay, then this, if this parent is also black, then there are two things. I don't like it actually, because it is too hard to write without errors. Okay, probably I can have a set, the set of vertices without black vertices without black children, so I can have. No, I don't want it. I don't want it. Okay, let's do it like this. Okay, never mind. So the only thing why I need BB is here. So what I need to do is, so again, BB is the number of vertices with the black parent and at most one black child. This is BB. So let's try and do it. So what happens when I add a vertex? A black vertex. So first of all, what about this vertex being BB? So if it is black, I need to check, is it true? That it has a black parent and at most one black child. This is a mess, but okay. Also, I need to check about this vertex. Oh no, 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 no. No, we don't want it. We don't want it. There should be some easy way. I need to somehow ban such situation. I need to somehow ban such situation. Okay, probably I can just calculate the number of vertices with big degree. or not? I need to somehow check that I have a degree of at most 3. Can I do it? Probably not really. Okay, one more way. So maybe I can store the set of vertices without black children, and also can store the minimum height of my vertex. And then the only thing I need to do is to check that the sum of these two distances is correct. Probably this is the best thing I can do. So we can, here we need also to store distances in the end. Okay. Whatever. So we say here that distance 2 is distance 3 plus 1. Okay, now we know all distances. Now I need to store this as a set. So here I need to remove px from the set. And here I need to put it in the set. And here I need to say that so if Lx black vertex without black children. Yeah. So if Lx, okay, let's like this. If addition is 1, then I need to add it. So I insert x ers. I need to erase x. So here actually I want either the number of such vertices to be 1, or I want it to be equal to 2, but then I want something good. So I want, what do I want? So I want to say, let's take distance of this vertex. Then let's take the distance of this vertex. So this is actually just, so this is the root. So this is what I calculated. Now I want to take this vertex and subtract it twice. So I want to subtract twice this distance. So minus 2 times distance of heights dot begin. So heights should be a multiset. And so if addition equals 1, then we insert distance of x here. Else we need to erase it. Great. So I subtract twice. So this way I calculated the expected number of edges, and it should be just be equal to BB. Yes. This is just something that should be equal to BB. Okay, now it's all no's. Now it's all just no no's, no's. Why? And it just don't want to go here. So BB is BV minus 1. It's true. What? Where am I? I think I am again reading the input incorrectly. So n should be 5, yes. Ah, I see. So now h is 0, 1, 2, 2, 3. 0, 1, 2, 2, 3, which is correct. So we have toggled this. Now h is 1, 2, 2, 3. Yes. Three is 4 minus 1, and BBC dot size. Ah, it's 0 for some reason. Ah, that's because I should have done this. Again not correct. What's happening? I broke my solution. I completely broke my solution. Black vertex without black children is 1 and 3, which is correct. So again, this size is 2. Let's look at distances. So 1 and 3. Distance of 1 is 2. Distance of 3 is 3. Yes, so it's 5. Now we need to subtract 2 times the distance of... Ah, not distance, but simply h. Dot begin. Okay, now yes, no, yes. Yes, yes, yes. No, no, yes. And again, the previous test. Previous test says no, no, yes, yes, no. Let's try to submit it. It took enormous amount of time, and I am really sad about it. Well, not good. Not good. Not good. "41 minutes and I spent 81 minutes. Well, happens. And also probably it will be tail if I'm not accurate enough, careful enough. Please, just pass all tests. I'm sick. Well, it's something sad. It's just sad. Let's look at problem F. I don't know. Yeah. It took good place, but not really. Yeah, so maybe we need to start looking at harder problems instead of F. Well, tourists spent 16 minutes, but maybe... Well, Orly spent 13 minutes. Maybe it is worth trying. So again, we know for each set we know what should lie in that set. No, for each set we kind of know what intersections are possible, what intersection sizes are possible. What? Can I just somehow iterate over all possible S? Let's just iterate over all possible sets S, and we want to check if it is possible. So when we do it, we iterate over all possible T, so it already spends 2 to the power n minus 1 squared to the power 2n, put it simply, and we check that it's correct. The problem is we don't want it because it's 2 to the power 40. So actually I have the following problem. So I have a set, I want to fastly understand fast what's wrong with it. I want to fast understand what's wrong with it. So what is the constraint T which does not work with it? Okay, let's go through. Oops. Let's go through all possible t's. Let's go through all possible t's. And for each t, so what is the maximum possible t actually? So f, not f of t, but what? V f of t. So v f of t maximum is simply the set of all numbers from 0 to t to the size of t. Yeah, so something like this. Oh, I don't know. This is a hard problem. Maybe I need to look at something else. We have two strings s and t of length n and m of lowercase English letters minus and star. We need to replace all occurrences of stars and minuses, observing the following rules. Minus should be replaced with any lowercase English letter, and each star should be replaced with a string of any length, which consists of lowercase English letters. Suppose that s and t have been transported into s prime and t prime. We want to check if there is a replacement that makes s prime equals t prime. Okay, this could be a standard problem with some sort of dynamic programming. With some dp over substrings, it's called. So actually, let's shrink them. So if we have two strings which start with the same letter, we can remove this letter. If we have two strings which start with letter and minus, we just replace minus with this letter and we do it. So let's shrink. At some moment, we have just two stars. So what do we have? We have a star we have a star and we have here something. And the same thing from the right side. Okay, there are several cases. So first of all, if we have star here, then we actually win. Because we can replace this star with whatever is written here and this star with whatever is written here. So this is easy. So actually, we don't have a star here. So that means we have a star here. And this means that we don't have anything like stars here and here. So here we have no star. Here we have no star. Because if we had, then with the same reasoning, we win. Okay, next. So if we have a star, here somewhere, then it's also easy. It's also easy because we can replace this string with this star with this string, this star with this string, and this star with whatever is written here. So it's also easy. So actually, we have two stars here and nothing at all here. Also, so here we have just a regular string, maybe with minuses. So we have just a string here, possibly with minuses. And here we have two stars. Okay. So actually it looks like this. So we have several strings here, and somewhere here we have stars between them. And here we have just a string. So we need to somehow, the only thing that we need is to somehow put these strings here and find them somewhere here. That's all we need. We need to somehow put them here, and then the stars can replace the remaining parts. So the question now is as follows. So we have a string which is a pattern, so it is something like a regular string but with minuses. And we have several other strings. We can check whether we can put these strings here. So actually we can do it greedily. So for this string, we want the leftmost position where it lies here. So we want the leftmost position for this string where we can put it. And then for this string, we again want the leftmost position where we can put it, etc. So basically it can be done with FFT probably. I always remember how it should be done. I also don't want FFT because I want the leftmost position. I am not sure if you need it for the leftmost position. So I have several strings, and I want to find their occurrences in one string, greedily, the leftmost possible position. Okay, can I do it somehow stupidly? So I have a symbol here. If it is different from this symbol, then I remove it. Then I go on. Okay, at some moment it becomes slow because I have a lot of minuses either here or here. And then something bad happens. Okay, let's try it with FFT. So what do I want? What do I want? I definitely don't want to run a whole FFT on this. Okay, to not run a whole FFT on it, I probably can do it portion by portion. So, for example, if I have a string of length s, I can find here a string of length at most 4s, for example, or at most 2s. And do it. And if I fail to find the leftmost occurrence, I just remove first s elements and go on. Yeah, it's probably something that works. And I have 12 seconds on this. Okay, so I go one by one with these strings. So how do I do it? I have a string and I have another string. I want to find all occurrences of this string within this string if I can have minuses here and I can have minuses here. If only I could remember that. Okay, I have 26 letters, so probably I can make use of some roots of unity. Yeah, I can probably make use of some roots of unity. So how do I do it? Let's say that A is omega to 0 power, B is omega to first power, etc. Z is omega to 25th power. And here it's vice versa. So A is omega to minus 0 power, B is omega to minus first power, Z is omega to minus 25th power. So I just find their what? Their inner product. And if I find exactly the length of this string, then I win. So if I have here, for example, minuses, then I need to replace them with zeros. And then I am interested in length minus number of zeros. So it should be the case. Okay, so what's wrong with this approach? The wrong with this approach is that I can also have zeros here. So I need to have the second FFT. I need to have the second FFT, which actually checks that. So that there are three ways that something is wrong to say. So I can have 0, 0, I can have 0, not 0, and I have not 0 with 0. I need to find the total number of such occurrences, and it can be done, probably. Yeah, it can be done. It can be done. Yes, it can be done. Okay, let's. It's such a huge pain, but let's do it. So N and M. N and M. Then I have two strings, and I read them. And I need to print yes or no. Okay, let's go. Actually, I think we can. Okay, so let's make two decks. Okay, so while s.size and t.size and s.front is not equal to star and t.front t.front is also not equal to star and s.front equals minus or t.front equals minus or s.front equals t.front. We say that s pop front and t.pop front. Actually not. So I need to do it like this. So, and here I ask if this is true, then I can make this pop fronts. Else, I need to return false immediately. Okay, then the same thing about the backs. So while s.size and t.size and s.back is not star and t.back is not star and s.front s.back if they are minuses and these backs are equal, then I pop back, else I return false. Okay, so now what? So first of all, let's check, is it true that S only consists of stars and T also consists only of stars? So if it is true and they both consist only of stars, we return true. Okay. Now we suppose that they don't only consist of stars. So if one of them is empty, we need to return false, because if one of them is empty, then it should consist only of stars. Then the other one does not consist only of stars, and it cannot be empty. So they empty. So okay. Now we need to check, is it true that s.front is star and t.back is star? Then we need to return true. And if vice versa, we also return true. So now if s.front is not star, let's swap them. Okay, now S starts with a star and ends with a star, and T does not. So let's check if T contains a star. So if C equals a star, then we return true. Okay, now T is just a regular string. T is just a regular string. So let's make a final T, which is T.begin, T.end. And let's make a vector of strings st, and let's fill it. So let's go from char c from s. So what do we do? Char c from s. So if c is a star, then we want to create a new string. What do we do? So if st.empty or st.back is not empty, then we say that st.emplace back, and then we continue. Okay, otherwise we need to say that if st.empty st.emplace back, nothing, and then we need to say that st.pushback st.back pushback c. Okay, now we just need to find in ft these strings one by one. So how do we do it? How do we do it? We have something like pointer, which is initially in 0. And ft is not empty, so so let's go through all strings. And we say something like jump SST. So in the end, if we want to say that return PTR is at least 0. So we just need to write a function which jumps. And the jump just moves this PTR somewhere. So if sst.empty we return, if PTR is at least a size of 15, then we say that PTR is -1 and return. Actually, not a size of ft, but what? If it is greater than a size of ft minus a size of sst. So if we have not enough characters in our string, we have to return from it. So otherwise, there is something harder here. Otherwise, it's something harder here. So what do we need to do? What do we need to do? So basically, we need to do the following. So we have some string s. we have some string t, which is long, and we have some pointer, ptr. If we need to take, we need to say that n is minimum of, okay, so let's do it. So let's say that int remaining equals this, I guess. No, minus ptr. So if remaining is less than s size of SST, or this, yeah. So we have some remaining characters in T, and we also block with 2s. So let's, actually we can say here while true. Okay, so let's say that jumping so I want to take some number of characters. Yeah, so let's say characters is minimum of remaining, and I don't know, 1 plus 2 times SST probably. I take this number of characters. Then I need to create a string which is just ft.subster starting with ptr and going this many characters. And then I need to take minimum occurrence of s, sst, and ttt. So if it is there, then actually what do I do? I say that ptr is simply of what? ptr is simply plus equals, first of all, minimum occurrence, and plus the size of SST. Great, great. And then I return. Otherwise, I have to jump. How much should I jump? Yeah, for example, let's assume that I took so for example, SST is 2 characters, and I have 6 characters. Yeah, so definitely I need to start here. I cannot start anyway here because I just can't. So I need to add 6 minus 2 plus 1. So I need to say to add chars minus size of SST plus 1. This is what I need to do. Probably 2 here. I don't know and I don't like it. Yeah, great. Great, great, great. So I just need to write this function, find minnow. So what does it do? It finds the first occurrence of S and T in T, and -1 if it's not there. Okay, let me think. So actually, if this size is at most 20, probably I need to do it easy way. So if t.substar starting with I and f.size equals this. No, I cannot do it like this. No, no, no. Okay, let's just not do it with easy way. Let's immediately make the FFT solution. So again, so what do? First of all, I need to make an FFT for minuses. I need to make an FFT for minuses. So let's say that I have vi minuses s. And minuses t. So minuses si is s I equals minus. And the same for t. Great. Then I will need to multiply them. Actually, no. Actually, here I don't want to reverse it. So then I need to multiply them. Yes? Yeah, I need to multiply them. Minuses s minuses t. Okay, let's start with copying this from Teambook, because unfortunately I don't have this in my team in my template, and this is enormously bad. Also need to write my own structure complex just now. So I need to have dbxy and I need to write functions like plus. So real times other real minus image times other image, and real times other image plus image times other real. Great. Okay, so now I need to somehow fix this. Does it already work? Ah, I did not write the function multiply. So vi multiply. So how do we multiply two polynomials? How do we do it? We make A and B. Then we need to calculate the... So first of all, okay, if A dot empty return A, if B dot empty return B, then we need to say int degree equals A dot size plus B dot size minus 1, and we need to turn ons like this, but before that, okay, probably here the FFT should be of size what? So the worst thing is that I have two strings of size 2 million, so it's like 4 million, so it's like 22. Which is definitely not good, but okay. So I need now to find the size of it, which is like count leading zeros of degree. -1. So I think like something like this. So it's this, and I put FFT dot multiply of A and B and ST. Yeah, and this returns some VD. Okay, I can put it here. They say here that answer I is round of answer I. Here, so basically that's a multiplication. Now I need to... Do I have actually time? I think there are 15 minutes left. No, actually not 15 minutes left. I still have some time. Great. Now let's make the actual pattern matching. So again, I have some string S, I have some string T, and I assign a root of unity to each symbol. Okay, then I want to make the matching. So let's actually do it, yeah. So I want to multiply complex arrays, don't I? Yeah, I want to multiply complex arrays. Am I able to do it with complex arrays? Let's see. Complex A, complex B, and I want to have complex here. So it's the same thing here. But here I don't put real, actually. Great. So actually I can also multiply two complex vectors. Great. So here, what do I do here? Here I need to do what? Vector complex S and T. So let's start with S. So here I need to say that S I is okay. So if Si is not a minus, then I say that actually this. Then Si is unity root of what? Which I don't want like this. Yeah, let's make it this way. So unity of this. And actually I want to take the conjugate of it. So here I need to write complex sub return real minus image. Yeah, so I also want vector t complex unity static, and if unity dot empty, cosine of I times 2 times m pi divided by c, and the same for sine. Great. Great? Yeah, great. Okay, so here I do this, and then I do it for t. So if ti is not minus, and ti is unity of si minus a without sub. So I have constructed s and t, then I need to multiply them. And I need to say the step, unfortunately, but the step is kind of same. So I need to do this probably. Okay, I don't like it. So let's do it again. So if a.empty or b.empty return nothing, else we say something like this. And we return multiply of a bst. So is it correct actually? So if dg is 4, for example, then this is 3, this is 30, and this is 1. No, probably 32. So this is 4, this is 3, CLZ is 30, and then this is 2. If dg is 5, then this is 4, this is 29, and this is 3. So yeah, it should be 32 here. Why are you telling me that? F of t. Because I didn't remove that step. What's wrong with... Okay, so I have multiplied them. Let's go now. So I have... actually... If t.size is for some reason less than s.size, then I definitely return -1. Right. So let's say that I iterate through this range. So I can return I for some reason. I can return I if something is true. So what should be true? It should be true that... So I take st I plus s dot size -1. Yeah. And I want to see at least something. At least the number of not-zero pairs. So how many non-zero pairs? It's actually s dot size minus 0 pairs. So how many 0 pairs are there? S dot size minus 0 pairs. So let's say int expected equals s dot size minus 0 pairs. And I want it to be at least expected minus epsilon. So expected minus this should be at most, I don't know what, but probably 1e minus 5. Then I can return e. Let's calculate 0 pairs. Equals the number of zeros in S plus zeros t minus 0, 0. So we need to calculate all three things. So let's start with 0, 0. It is simply Total minuses. This. Now we need to calculate 0s and 0st. Okay. And the same thing here. Great. I think we've done it. At least we should have done it. Okay, now I need to make multi-test without reading this. And let's make the multi-test. No, yes. No, no, yes. No, yes. No. No, yes. It's actually always no. So this is bad. Okay, this is no. Now let's see. Look at yes. So this should be kind of easier. So now S is just a star and S is just an empty thing. Ah, and it should have returned true. Ah, so now it's true. So now it does not work. Okay, let's see where it happened. Ah, okay. No, yes, no, no, yes, actually. Actually, it worked. Let's try and make some other tests. So, for example, A, B, C, D, E. And here I have A, B, C, D, E, and something. It said no for some reason. Although definitely I have A, B, C, D. Why did it happen? Okay, so we have PTR. And I want to look at S and T. Let's look at ST, which is A, B, C, D, A, and empty for some reason. It shouldn't be empty. I don't like it. Why is it empty in the end? Ah, okay. While st dot size and st.back.empty. Probably we can say st.popback. But it will not help. Now st consists of a, b, c, d. Okay, ptr says 8, 15, -1. So it did, after b, it did not find c. Ah, because cd. I need cd. Okay, now it's yes. What about C minus here? Will it work with C minus? Yes. What about just two minuses here? Or with minus D? It should all be yeses. Yeah. Let's try. Maybe it works. Although probably not, but we'll see. Oh no. Oh no. Oh no. Probably wrong answer, test 6. No. Wrong answer, test 7. Actually, it should work in parallel, so probably I will have now immediately something like running on pretest 30. Yeah, guys are monsters who do it immediately. What do they usually get? Pretest on 27. Okay, so probably we'll have tail on test 27. 24. Okay, there are a lot of sad verdicts here, but we will not have any of them. Actually, let's look at status. No. Wrong answer, pretest 31. What? Wrong answer on pretest 31? What? Am I the only one to do that? Okay, we need to somehow understand what happened wrong. So first of all, let's see what happens if we have cosine of 2 times m pi divided by 26. Okay, so it's like 2 to 3 hundredths. So this means that actually the error here should be at most strictly less than 2 to 3 hundredths. For example, I can actually put here this and it still works because it can't happen that this was caused by problems with the polynomial. Yeah, because actually if you look at it, maybe I need to make long double. Can I do it with long doubles? I probably can do it with long doubles. What is this? Well, let's try. Let's probably try. So what do I need then? Need to say here cos L and sin L. Here I probably don't do anything. Here I probably don't do anything. So there where I define what VD is, probably I need to say long double. No, I don't want it. So instead, let me just say that I have that I have a VLD here. So LT, VLD, LT. Ah, no, 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 no. I just need to take vector TB here. Well, I always need to say vector TB, and that's it. That's the key. That's the key. That's the key. Okay, and here I also need. Okay, that's it. No, yes, 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 no, yes. Okay, let's try again. I don't know what caused it, but also I just don't like that my solution immediately becomes much slower. And it also will take a lot of memory. I think it will take a lot of memory. So it's an easy tail. Maybe I will. Yeah. Yeah, not a good idea to do that. Okay, let's probably try to shift back to doubles. I don't like not doing anything, but I don't know. Do people often solve G but not F? No, actually they don't. They just solve F, and after that they solve G. Usaga did it another way. Okay, let's see if it helped with pretest 31. No, it did not. Oh my god. Why is it wrong on pretest 31? Okay, let's go back and see. What do we do here? Find uns. Maybe I need to make a stress? No, I don't want to make a stress because it will kill me to make the stress in this problem. Or not. Or is it fine? No, I don't want it. So I have a deck of chars S and T. So again, I go from front, and while they are both non-empty and not stars, then I compare if it's fine to remove one character from the beginning. And then I do the same thing from the end. After that, I either have an empty thing or I have star in the beginning and star in the end. Now, if they both consist of only stars, then I win. Otherwise, if one of them is empty, then I lose. Yes. Now, if S has a star and T also has a star, but in the end, I also win. If and vice versa. Otherwise, let's assume that S has both stars in the beginning and in the end. And if T also contains a star, then I win. Okay, now I have a PTR. PTR says that I want to find the substring of S. So I will jump. So I know that this substring is at least PTR. So what do we do? If this is empty, I return. It's fine. Otherwise, I have these many characters. And if the number of these characters is less than SST or PTR is negative, then I cannot do anything. Okay, now we say that I take this many characters, either remaining or 2 plus 2 times size of SST. Yes. Then I take this substring of PTR, starting with PTR and chars characters. Yes. Then I try to find SST and in TTT. And if I was not able to do it, I need to do this. Yeah, and this is correct. But if I found it, then I need to add minoc plus s size of SST. Why? Because firstly I need to jump to minoc, and then I also need to jump over this string, SST. Yes, and I do it, and I return just because. Mm-hmm. Mm-hmm. So actually I just need to write this function correctly. Find minoc, I need to write it correctly and that's it. Find minimum occurrence of S in T. So if T dot size is less than S dot size, I return -1. Otherwise, so what do we have here? We have only small English letters, minuses and stars. We also don't have any stars, only minuses. Yeah. Ah, it's stupid because this should not be like this. It's very stupid. Instead of that, I need to take then only zeros in this prefix. I only need to take the zeros in prefix. So let's do it. So I have vi zeros t prefix of size t dot size +1. And I need to say here that zeros t prefix of I +1 is zeros t prefix I plus this. Okay, then I need to say here that int zeros t is the number of zeros in this prefix minus the number of zeros in this prefix, and only this is zeros t. Great. Amazing. Just amazing. Oh, a roller coaster. A roller coaster of emotions. But maybe we'll get somewhere. So again, I believe that we will easier win 31 tests. So we just need to where's my submission? Why can't we see it? Okay, 31st test. This is the ultimate thing. Can I defeat 31st test? And I can. Because my solution is correct, isn't it? Probably I need to think of something in problem F, but it is problematic. I cannot solve problems so fast, unfortunately. Did someone hack something or not? Maybe in our room there is something that can be done. $75? How can you get 75 points for... You really can get 75 points for a problem? This looks sorry, but this really looks miserable. How can you get 75? 30% of a problem if something is really bad. Why? And what can I do to prevent it? Okay, are there really people with test 50 problems? Yes, there are. So we need to somehow make it faster. To make it faster, probably we can put here 3. Yeah, probably we can put here 3. Okay, probably, I don't know. Also, I can get rid of long sinus and cosinus. Probably regular sine and cosine are enough. What else? What else can I do to speed it up? I probably cannot make FFT faster. I also can merge two runs of FFT in one, but this can only be done if I don't have a complex FFT, but I have one, so probably not. I can also make or work with floats, but working with floats sounds like a bad decision. Yeah, so I'll have something like 2 million FFT, 2 million long FFT, so there are 2 million. Well, maybe it's worth trying. So can I just put here float? I probably can. Okay, so the 51st test. Did it help me by chance? No, it did not help me. Well, it helped me, but now I need to pass 30 more tests. Do we believe in it? Budalnik solved the problem? Budalnik did not solve this problem. For now. But even if we pass all these tests, probably we'll also... We are also prone to failing it. Okay, so somebody time limited on test 69, so we also have a chance of doing it. But if not, then probably we're good. Yeah. Also wrong answer test 70. How are you all guys doing it? Wrong answer test 70 is something that will destroy me. Also, how do people do it? Okay, they have very fast FFT probably, so they can copy FFT from your super judge and be happy about that. Oh, it's a nervous problem, guys. It's really a nervous problem, guys. '83, 84 tests, so we only have 5 last tests, and we're good. Unfortunately, I lost like 300 points, so this is bad. I lost 300 points. Oh, I'm jealous. I also would like to be able to solve it in 3 seconds. What? Are you joking? 200 milliseconds of this problem? Okay, I don't feel confident at all about this. No, this is not good. This is not good. Oh my god. Oh, this is not good. This is not good. Okay, let's believe in the best. Let's believe that this is what works for some reason. But yeah, this is this is not the situation I would like to be in. Okay, probably I will fail system testing, but 300 milliseconds, oh, even 230 milliseconds. Like if we add these two solutions, it's still not tail, but this is very near tail. Ah, what I'm doing? This one, of course. Well, okay, okay. It's not good, but let's hope that this is correct solution. Let's go through let's go through all problems. I will now explain them. Okay, problem A. Bazooka and Mocha's array. Or Mocha, I don't know. Mocha likes arrays, so before her departure, Bazooka gave her an array A consisting of n positive integers as a gift. The best gift ever is to give someone an array of n positive integers. Mocha wants to know whether array A could become sorted in non-decreasing order after performing this operation sometimes. So you split the array into two parts and you swap these two parts. So here is your array. And what you can do is you can split it into some two parts, and then you can swap these two parts. Or to put it another way, you put the first half after the second half. What you should know about this, so how many just, you can clearly see that this is some permutation of these elements. And there are n factorial possible permutations. So the question that you might ask yourself is, are all these n factorial permutations reachable from the initial one by these operations? The answer is no. Among all these permutations, you can only get n different permutations. You cannot get all n factorial of them. And this is because actually there is a beautiful way of looking at this operation. Let's just say that we have all our elements arranged on a circle. Something like this. Okay, so we have all these elements on a circle. So actually, if you spin this circle, then you don't know your array because you don't know where it starts. But if someone says you that this is the starting element, then you know how to continue it. In other words, you can cut this circle in some point and it becomes an array. Now let's see what the operation does. The operation does the following thing. It takes some element ak, or better say a border between two elements, ak and ak plus 1. Then you cut the array here, and then you put this thing not after the element ak, but before element a first. Notice that on this circle nothing really moved. It is still in the same position. Yeah, you should have, so in this picture, yeah, this is ak plus 1 and this is ak. So in this picture you need to move this first block after this second block. Yeah, but in my picture you don't need to do it. Instead you simply leave it in the same place as it was, but instead you remove the cut. So now you don't cut the array in this part, you cut it here. Now the array starts at element ak plus 1 and ends at the element ak. And if you look at the picture like this, then you see that the only thing that you can affect is the position on this circle where you cut this array. So there are n possible cuts, here, 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 etc. And you just choose in which of these places you will cut. Okay, now the problem is quite straightforward. So you have n elements on a circle, and you need to answer on the question, can you cut it somewhere such that this array is non-decreasing? So you have a circular array, you need to make it a straight array which is non-decreasing. And you can easily solve this problem. How to do it? So intuitively, you need to start from the minimum element. Yeah, so you need to start from the minimum element. So you need to check, so you need to find the minimum element and to check if this part is non-decreasing. Then also element an is at most a first. And then this is also non-decreasing. The problem with this approach is that the minimum is not unique. You can have several different minima. Well, they are not different, they are the same, but they can be in different positions. In this case, so actually if there are two minima, and something greater than minima is both here and here, then the answer is no. So whatever you do, you cannot get rid of this firstly increasing and then decreasing, and then again this increasing, this decreasing. This cannot be happening in a cyclic shift of a non-decreasing array. However, it can be a case that you have several minima in a row. So you can have several minima in a row. In this case, you need to start from the first one of them. But this raises a question. What is the first minimum if you have a cyclic array? Because if you just take the first minimum as it is in this initial array, you have a problem. For example, in an array 2, 2, 3, 7, 2, this is the first minimum. But in this ordering, you lose because actually you could have started from this element and then it would work. You did not. You started from this element. So you need to somehow find the first, cyclically first minimum. So actually there are two approaches that I see sensible. One of them is to try two positions. First position is this one. So find just the first minimum in our array. How can it be not the first minimum cyclically? If you have also some minima in the end of the array. Yeah? So actually you take the minimum of your array first, and if it is the 0th element, then you try from the end to find this minima here. So you check if this is a minimum, if this is a minimum, this is a minimum, etc. And at some moment you stop, so you see a bigger element, and you start from this element. So again, find the minimum, and if it is the 0th element of your array, you start going from right to left from the end of array and search for the last minimum in this direction. There is again one tricky case when you only have minima in your array, so all elements of the array are minima. In this case, the answer is yes. The second approach is my approach. So what I did is I took my array and I duplicated it and put it after the end of the previous copy. So now I have two copies of size 2n, and only thing I need to do is to find a subarray of length n which is non-decreasing. So I need to find a non-decreasing subarray of size n. If I can do it, and only if I can do it, then you can rearrange your array for it to become non-decreasing. How to do it? So there is a simple greedy algorithm which finds you the longest non-decreasing subarray of your array. What does it do? It goes through elements one by one and stores two things. It stores the maximum non-decreasing subarray that it has already seen. And secondly, it finds maximum non-decreasing subarray that ends in the current element. So you have some current element, and you find the longest non-decreasing subarray which ends in this element, and you find the global non-decreasing subarray. Now, what do you do when you consider a new element? So this is car prime. So if car prime is at least car, then actually you can, let's call this M and this C. So you can say plus plus C, because your current non-decreasing subarray is increased by 1, by length. So, but if car prime is less than car, then you cannot do it. And instead you start over. So you say that C equals 1. And after each operation, you just say that M is maximum of M and C. So this is the simple procedure that you can do and that I did. So this way you can find the longest non-decreasing subsequence subarray, and you check that its length is at least n. That's what you do. Okay, I think that's it for problem A. And we can go on with problem B. We can go on with problem B. we can go on with problem B. Mocha likes arrays, so before her departure, 378QAQ gave her an array A consisting of n positive integers as a gift. Array is beautiful if there exists two numbers I and j such that all elements are divisible by either AI or AJ. Determine whether A is beautiful. So let's have this array. Yeah. So let's say that a set A divides this array if each element from AI is divisible by some element of A. So set A divides our array if each element of our array is divisible by something from the set A. So the question is, does there exist a set AIHA which divides the array? This is the question. So notice that let's take our array and let's find the minimum element from this array. So let's AI be the minimum element of our array. Notice that it cannot be divisible by anything except itself. Yeah, because any other element which is not equal to AI, it is bigger than AI. So AI cannot be divisible by AI. So if you really want A to divide our array, it means that A should have some element which is less or equal than AI. But since we have A consisting of only elements of our array, this means that we have to have the minimum element in our array. So if AI is the minimum element of the array, then we have to have it here. Okay? Okay, now let's remove all elements which are divisible by AI from our array. You can just ignore them, or you can remove them, or you can construct a new array which only consists of elements which are not divisible by AI. And then actually absolutely the same argument applies. Almost the same argument. Okay, let me draw it. So we have two types of elements which are divisible by AI and which are not divisible by AI. So there are some elements and they are already satisfied with A containing AI. But there are also elements which are not divisible by AI and they are not satisfied by A yet. So we need some new element. For example, let's take some AJ. Notice that AJ cannot be satisfied by any of these elements. Because if it is satisfied by some element AK, that is, it is divisible by some element AK, then AK divides AJ, but AK is divisible by AI. So actually AI divides AJ, which is not true. As you see, AJ is not divisible by AI. So actually, since we have AI in our set, it does not make any sense to put any other elements from the top set from X. So you don't take it. So to satisfy elements from the lower set, it actually only makes sense to use the elements of lower set. And because of that, you can repeat absolutely the same thing. Let's take the minimum element AJ here. Nothing can divide this element AJ from the lower set except AJ. So you have to just take it. Okay, now we have two elements. Actually, if in the statement it was said that X should contain at most A should contain at most 10 elements, then we could continue like this. But A should contain 2 elements. Yeah, 2 elements. So actually we stop here. Now we have 2 elements, and we just need to check that every element of array A is divisible by either AI or AJ. And you just do it in linear time. So to recap, you find the minimum element in your array, you understand that it should be AI, and then you find the minimum element in your array which is not divisible by AI, and you understand that it should be AJ. Now you have 2 elements, and you just check that everything is divisible by AI or AJ. It also can happen that AI is... It also can happen that AI is... it divides all elements of array, so actually AI is enough. You just don't need... You even don't need AJ. But in this case, you just take AJ any element, and it's fine. So you just make this simple checks in linear time, and you're happy. Problem C. So we have an array consisting of n positive integers, and we can replace a subarray with a median of this subarray. Actually, with r minus l plus 1 copies of this median. And we need to find maximum possible median after all these operations. Median is defined as middle element after sorting if the number of elements is odd, and if the number of elements is even, then there are 2 middle elements, and you take the lower one, the 20, the smaller one. Yeah? So again, you have an array, you can take a subarray, and you can replace all of its elements with occurrences of the median, with repetitions of median. So actually notice that if the median would be the upper element, yeah, that is m plus 2 over 2, this element, among m elements. Yeah, for example, in array 2, 4, 6, 8, it should be 4 plus second over second. So third element, it would be this one. So bigger of 2 middle elements. Then the problem would be very easy. You just need to find the maximum, and this will be the answer. Why is that? Because you can take the maximum, then you can take the neighbor element from the right side, and you can take this array, and you just turn this element also into a copy of M. Then you continue like this to the right, and then you continue like this to the left. And that's it. You have all numbers equal to the maximum. But this is not the case. You cannot take this element. need sometimes to take this element. Well, always you need to take this element. Unfortunately, we'll have to solve the problem. And actually, I did not prove my solution. I kinda felt like it's fine. So you can notice that, so first of all, the problem is monotonic. So if you just increase some element, then the answer cannot decrease. It can only increase. If you decrease some element, then the answer cannot increase. It can only decrease. It's easy to see, for example, by induction or any way as you want. For instance, it means that you never want to take a two-element array. Yeah, if you take a two-element array, then actually it is replaced with two occurrences of minimum. So minimum of AB and again minimum of AB. This means that you just decreased one of the elements. You never want to do that. Also, it never makes sense to apply this operation for one element because it just does not change. So operations with one element arrays and two element arrays don't make any sense. And now the question, what about three element arrays? Well, there is only one situation where you want to apply an operation to a two element array. It is when there are just two elements. So your array consists of two elements. You don't have any choice but to simply apply this operation to both elements and get minimum of A and B in your answer. Okay, let's assume that n is at least 3. Yeah? In this case, you want to so you'd never want to apply operations of length 1 or 2, but maybe we can apply an operation with length 3. And if you think about it, actually there is some strategy which gives some not bad result. Yeah? So notice that, assume that you liked some array of size 3. Yeah? You see some array of size 3, ABC, and assume that you liked it. You think that median of ABC is quite nice. It is it is big, and you like it. What you can do then? Then actually you can win. So assume that it is M. M is median of some 3 consecutive elements, and you like it. So let's, with first operation, replace all these 3 elements with M's. Now you can notice that you can actually replace all the remaining elements of the array with M's. And this is straightforward. You just take, for example, this element and put here M. You apply the operation to these 3 elements and you get MMM. Then you apply operation to these elements and again again get MMM. And so on. And here also. So if you have, actually always, if you have 2 equal elements in your array adjacent, then you can spread this value across all your array. So the moment you see some 3 elements with big median which you like, you can apply the operation to these 3 elements, and after that you can make all elements equal to this number M. There is still no system testing, yeah. Okay. So now we can get the following number. Maximum among all i's from 0 to n minus 3 of median of AI, AI plus 1, AI plus 2. This is what we can get. Actually, this is the answer. So what you really need to do is you need to iterate over all subarrays of length 3. In each of them you need to find the median, and you need to find the maximum such median. Question is, does it make sense? Does it make sense to do it like this? I mean, is it the correct answer? Or it can be bigger? And I believe the answer is you cannot get bigger than this. Let me think why it is true. It is true because I think I will be able to prove it to you. So again, assume that this number is m. What I want to prove to you is that you can never obtain a number which is greater than m. So this is my theorem. So no operation can result in some numbers n which are greater than m. So this is impossible. Okay? Let's prove it. Let's actually prove it. So let's find the first operation which did it. So you made some operations and you found, and after that you made an operation in which the median is greater than m. Okay, let's find the first such operations. So you probably made 0 or more operations in which you generated numbers which are at most m, and only then you made the first operation which generated a number which is greater than m. So let's find the first such operation. So in it, the median is n, and the number of elements is k, for example. How can it be that the median is n? So median is n. This means that there are at least k, let me think. K plus 2 over 2 elements which are at least n. Okay? So for even k, there are at least 1 plus k over 2 elements which are at least n, and this is true. For odd k's, there are k plus 1 over 2 elements which are at least median, and this is also true. So you made some operations, and you have this. Okay, notice that actually during the previous operations, yeah, so you have some operations op1, op2, op3, etc., opt minus 1, and opt. So opt is the first operation which generated element which is greater than m. So during these operations, only elements which are at most m were generated. And since they are at most m, they are definitely strictly less than n. Okay? Since this is true, let's assume that they just never existed. Yeah? So why is that? If after these operations there are so many elements which are at least n, and these operations never generated elements which are at least n, then before these operations, you also only had elements which are at least n. So we can pretend that no such operations took place. At least, at the very least, we can make them after this operation. But actually, we can simply so since I'm analyzing this situation, I'm not actually removing these operations in the sense that, again, we have a subarray in which there are at least so many elements which are at least 10. There were some operations which could only make this worse, which can only decrease the number of such elements. This means that before these operations, it was also true that there was at least so many elements which are at least 10. Okay, so let's analyze, let's pretend that we make this operation as the first operation. So we have an array, we have a subarray of length k, and there are at least k plus 2 over 2 elements, which are at least n. But what we know is that among any 3 elements, at most 1 which is at least n. Because if there were 2 elements which are at most n, then median would be at least n. And if the median would be at least n, then actually this number would be greater. This number would be n, not m. So if we draw an exclamation sign in each element which is at least n, then among any 3 elements there is at most 1, among 3 consecutive elements, there is at most 1 exclamation sign. So the distance between any 2 exclamation signs is at least 3. The difference between indices. So now the question. You have an array. In this array, there are in some places, exclamation signs. And in any 3 consecutive elements, there is at most 1 exclamation sign. Can it be that in this array of length k, there are at least k plus 2 over 2 exclamation signs? The answer is no, it cannot be like this. It cannot be like this. It's easily seen by induction. Yeah, it's easily seen by induction. So in a base, k equals 2. If k equals 2, then we need at least 2 plus 2 over 2 equals 2 exclamation signs. But this means that in our array of size 2, there should be 2 exclamation signs, and this is impossible. Okay? Also, let's make as a base case k equals 3. This means that we expect 3 plus 2 over 2 equals 2 exclamation signs among 3 elements, and this is also impossible because in any 3 elements there is at most 1 exclamation sign. Let me write again the statement. So it would be more clear what I'm trying to prove to you. So again, let's say that we have a binary array consisting of spaces and exclamation marks. Among any 3 consecutive elements, there is at most 1 exclamation sign. We need to prove that for any k, at least 2, in any k consecutive elements, there are less than k plus 2 over 2 exclamation signs. This is what I'm trying to prove. Because if we prove it, then actually it's impossible to make the first operation in which an element of which is at least 10 generated, just because there are no such subarrays. I prove it by induction for n, and base case is k equals 2 and 3, and they are shown here, and they're pretty easy. So you cannot have 2 or 3 elements. Okay, also binary array of length at least 3. So base case is 2 or 3. In both of them, you need at least 2 exclamation signs, and you cannot have them in such a short array because of this part of the statement. So let's make the induction step. Let's take an array of size k. Okay, let's take last 2 elements. Among them, there are at most 1 element because it's set in the basis of the induction. Among these elements, there are at most, so there are k minus 2 elements in this subarray. And by induction, we know that there are less than k minus 2 plus 2 over 2 equals k over 2 elements. So here there are at most this many, less than this many exclamation signs, and there are at most 1 exclamation signs. So in total we have less than 1 plus k over 2 exclamation signs, which is simply k plus 2 over 2. So the induction is proven. So actually you cannot make the first operation which generates element which is greater than m. But this means that you will never generate any element which is greater than m. And this means that simply, if not elements are equal, then you will not be able to make them equal to something which is greater than m. And if all elements are equal, then you simply don't need to do anything, so you also don't do anything. So actually you cannot make the answer greater than m. Hence the answer is this number. Again, maximum of median of subarray of size 3. Maximum among all such subarrays of size 3. This is the answer. Okay, the system testing says that problem C is solved. Problem D, paint the tree. So we have 2 pieces on the tree. So we have a tree. And there are 2 pieces. Let's call them red piece and blue piece. Each time a red piece enters, initially all vertices are white, for example. If I draw black, this means that this is white. So if a vertex enters if a red piece enters some vertex which is white, then it becomes a red vertex. If red piece comes in any other vertex, it doesn't change it. And the blue vertex, if it comes into red vertex, it makes it blue. But if blue piece comes into any other vertex, it does not change. So again, let's draw the diagram. So white vertex can become red if a red piece visits it, and red becomes blue if a blue, becomes blue if a blue piece visits it. So these are two transitions which are possible. Good. So the question is, we want to make the whole tree blue. What is the minimum number of operations to do that? And the red and the blue piece, they alternate turns. So first red makes something, then blue makes something. Then red makes something, then blue makes something, etc. So let's first imagine that there is no blue piece. There is only red piece, and you need to make the whole tree red. What is the minimum number of operations? The answer to this question is known. So first of all, let's assume that the problem is to make the whole tree red twofold. So you need to visit. Let me think what I meant. Actually, no, not twofold, sorry. The question is you need to color the whole tree and then return to the initial vertex. So again, you need to visit all vertices of the tree, then return to the initial vertex. And the question is how many steps you need to do that. Actually, the answer is 2n-1. Because actually to visit all vertices, you also need to traverse all edges. Yeah, again, so I think I need to write everything. So the first problem is we have a piece in vertex A. So what do we need to, what we can do? We can move a piece to adjacent square, to adjacent vertex. And we need to visit all vertices and return back to A. Question is, what is the minimum number of moves? So in this case, I claim that the answer is 2n-1. That is double the number of edges of the tree. To prove that the answer is this, we need to prove two things. That the answer is at least 2n-1, and that it is at most 2n-1. And we will prove both of them. Let's start with this thing. How to prove that the needed number of steps is at least 2n-1. To do that, you need to understand that to visit all vertices, you need to go among all edges. Because if you ignore any edge, then you cannot get to the other side. Yeah. So, for example, if here we have a vertex A, actually any edge in the tree is a bridge. That is, if you remove this edge, then the graph becomes disconnected. And if this graph becomes disconnected, you cannot get here. So you actually need this edge to get here. So actually, you will have to go along this edge, and then you will have to come back. So for each edge, you will have to go at least twice through it. One way away and another. And the other. That means that for any edge, for each edge, there are 2 moves associated with it. And since there are n-1 edges, in total you will have to make this many moves. Okay, let's prove that the answer is at most to n-1. Actually, this is called Euler tour of a graph, and of not a graph, but of a tree. So if you double each edge of a tree, yeah, that is, you draw it like this, then it becomes an Eulerian graph. That is, each edge degree is each vertex degree is even. Firstly, and secondly, it is connected. And in any Eulerian graph, there is an Eulerian cycle, which visits each edge exactly once and returns to the initial point. This is a famous theorem by Euler, and if you apply it to our situation, you see that there is indeed an Eulerian cycle in this multigraph. So actually you can visit all vertices and all edges and return to the same vertex in this many moves. Great. Now the second question. It starts the same. These can go starts in vertex A of a tree. It can move to adjacent square, and again not square but vertex. What is the minimum number of moves to visit all vertices of the tree, but not necessarily end in A. So, compared to the previous question, you needed to return back to A in the end. But in this question, you don't need to do it. So you can end in any vertex you like. This is also a very known question. And the answer is... so let's say that D of A is the maximum X such that there exists a vertex in the tree that distance between A and B equals D of equals X. So if B is the farthest vertex from A in the tree, then D of A is the distance to this farthest vertex. So if we have this notion, then answer is 2n-1 minus D of A. Again, there are 2 things. There is this thing and this thing. We again can prove both of them. Let's start with this one. Why you need to spend at least this many steps? So you have a tree. Here is your vertex A. You started in it, you moved somehow, and you ended in some vertex B. So in the previous step, B was required to be equal to A, but in this case, it's not required. Now let's forcefully return from B back to A. If you do it now, you have the solution to the previous problem. And because of that, so ans is transformed into ans prime, which is the answer to previous problem. Ans prime is simply ans plus distance between A and B. As we know, the answer to the previous problem should always be at least 2n minus 1. Therefore, answer is at least 2n minus 1 minus distance between A and B. But notice that this is the distance between A and some vertex, and d of A is the distance between A and the farthest vertex. The distance between A and B is at most the distance between A and the farthest from A vertex. So this is at least 2n minus 1 minus d of A, which is what we wanted. So this is proved. Now let's prove this part. That actually answer is at most this number. To prove that, let's look at A. And the farthest from A point. Let this be the path between A and B. Now let's again make the same trick as in the previous problem. That is, let's double each edge of our tree. Except this path. So the path between A and B is untouched. We don't do anything to it. But to every else vertex, every remaining vertex, we double the edges. For any other edge except this path. We double the edge. This is what is maybe called a semi-Eulerian graph. In this graph, each degree is even except for A and B. Because for A and B, you doubled every edge from A except one. And for B, you doubled every edge of B except one. And inside of path, you doubled each edge there except two edges. For example, for this vertex. Yeah, there are several edges incident to it, and each edge was doubled except these two edges, which were not doubled. So the degrees of all vertices except A and B are even. And this, and the graph is still connected. This means that there is this Eulerian path, which starts in A, visits all vertices and all edges, and ends in B. And this is what we need actually. This semi-Eulerian path consists exactly of this many edges. So we have answered questions A and B. But now we have the harder question. So now we have a tree. And there are some vertices A and B. And you need to visit all the vertices in our tree. Okay? So this is A. This is B. So actually, the optimal algorithm to this problem is as follows. Let's find the vertex in the middle between A and B. What is in the middle? This means let's take this path between A and B. Let's say that it is of length D. And let's find a vertex such that this length is D over 2 up. So actually what you need to do is you need for A to come here, for B to come either here or here. Probably it will be here if D over 2 floor is not equal to D over 2 ceiling. And after that, yeah, when A is here and B is here, you just apply the previous. So let's call this vertex M. You apply the previous algorithm where you just visit all vertices. It will take n to n minus 1 minus d of m, as in the previous problem. And plus you needed d over 2 ceiling steps to just come here. So this is the optimal answer. Now the question is why it is optimal. Why is this algorithm optimal? And unfortunately, I don't know. I wasn't able to prove it during the contest. Probably. So it should be true. And yeah, now my solution is now running. So maybe we will see now that it is incorrect. But I hope that it's fine. Well, this is so sad that my solution might just fail system testing because it's near the tail. I don't know, is there editorial? Editorial is available. Let's see if they prove this. This is what they do. This is what they do. Okay, so what they say is actually answer is, so the first moment that some vertex is painted blue, so time to paint first vertex, let's call it V, blue, plus of course to n minus 1 minus d of V. So it's kind of divided into two parts. To paint some vertex V in the blue color, and then to run the algorithm for this vertex V. So answer is simply minimum among all vertices V in our tree of time to paint it blue. How much does it take to paint some vertex blue? Actually, you firstly need to visit this vertex with A, and then you need to visit this vertex with B. And this is, it can be greater, but this is at least no, it's gonna be, yeah, it is at least distance between A and V. And distance between B and V. And then you need to spend like 2n minus 1 minus d of V. Great. So actually what I want to prove is that always maximum of distance A and V and distance B of V and V plus 2n minus 1 minus d of V, it is always at least the same thing for M. And for M, it is d plus 1 over 2 plus 2n minus 1 minus d of V, d of M. So this is what we want to prove. Let's cancel this out. Now we want to prove that maximum of distance A and V and distance B and V is at least d plus 1 over 2 minus d of M. Minus d of V. Okay. So let's assume that d of V is some distance between V and some vertex U. So U is the farthest vertex from V. So here we can actually, instead of d of M, take d plus 1 over 2 minus distance of M and U. Why is that? Well, it's easy to see that this inequality holds because d of M is at least this distance. And you have minus here. Yeah? But so if you prove this inequality, then you automatically have this inequality. This one. So let's prove it. So again, we want to prove that maximum of distance of A and V and distance of B and V is at least d plus 1 over 2 plus distance V and U minus distance M and U. Okay? Okay, let's somehow think about that. So here is A, here is B, here is the middle, which is M. Well, actually, there are two cases. So if you remove the vertex M, then there is a left part of this tree, which is nearer to A. And there is the right part of the tree, which is nearer to B. And we can consider two cases when V is here and when V is in the left part or V in the right part. So let's consider both of them. So if V is in the left part, then actually the maximum is this one. So distance of B and V should be at least d plus 1 over 2 plus distance between V and U minus distance of M and U. Yeah? Why is V in the left part? Actually, because if you consider the path from V to A, it lands somewhere here and then goes here. So this is the path between V and A. Yeah, so the length here, let's call it L. The length here, let's call it, I don't know, T. Then this is t plus L. So this is d minus L. D plus 1 over 2. Plus distance between V and U. I don't know where U is. Actually, I really don't know where U is. But the difference between these things is really at most this distance. So let's replace it with this distance. Let me think. Okay, probably something like plus t minus this distance, which is d over 2 minus d minus L. Okay, this is what we want to prove. So if we remove t, then we have this. L is at least d plus 1 over 2 plus minus d over 2 plus d minus L. No, this does not make sense. It's other way. Plus this and minus this. So this, and this. Okay, actually it's very known fact that d over 2 plus d plus 1 over 2 is simply d, and L is L, so actually this is just equality. Okay, this is the first case, when V is in the left part. When V is in the right part, I can also write to you, but I think it's quite similar, so it's an exercise for you. So I have proven this. Yeah. So therefore, you always want to take the middle vertex M of this path, and starting in it, you just traverse through the tree. So the answer is, as I said, d over 2 ceiling to get from B here, and plus the usual answer to this problem, which is 2n minus 1 minus d of V. Minus d of M. Here, the answer is great. Do we have some system test failures? Still no. Problem E, chain queries. You are given a tree of n vertices. Initially, all vertices are colored white or black, and we are asked to perform Q queries. Toggle the color of vertex U, that is, if it was white, change to black, and if it was black, change to white. After each query, we should answer whether all the black vertices formed a contiguous path in our tree. And we should do it fast. How to solve this problem? Actually, my solution was quite a mess. We'll explain it, and then I'll look into the editorial if there is something nicer. So, actually, what I am looking at is, well, if you're... Sorry. Okay. You need to understand if some black vertices in your tree form some structure. what we usually want to do is we calculate some numbers which explain to us how the structure looks like. And if these numbers fit into the picture of it being on a path, then we say yes. If they don't, we say no. Fortunately, if we don't do a good job of thinking of these numbers, which are also can be called features. So if the set of features is not complete, actually it might be the case that all your numbers say that it is a path, but it is not a path. And this is what happened during the contest and what I noticed. Also, the features should be somewhat calculable. So you calculatable, computable. You don't want them to be too hard. Okay, so what I did. So you have some black vertices and some white vertices, and you toggle sometimes them. So in the end, they might form a chain. Okay, first of all, the chain should be non-empty. How do we understand if the chain is empty or not? So let's store a number which is called BV. Initially, okay, first of all, initially I think that all vertices are white. Then I make for each one among the numbers in this array, I make a toggle, and only then I apply these operations. So I assume that initially all vertices are black, are white, and only then I make these toggles. So when I say that initially BV equals 0, that is, there were 0 black vertices. This is not because in the statement actually the number of vertices was 0, but because I made it 0 and said that then I will make some toggles to make the colors same as in the array C. So initially the BV is 0. How to calculate this, how to update this number? We also store the array, which can be called, for example, B. In my solution it was L for some reason, but it should be called B, which means that, or C actually, you can call it C. We also maintain array C, which says if the color of vertex is 0 or is black or white. So when you are set to toggle a vertex, you check if it was 0 or 1. Then you understand what happened. Then you can calculate the number, which can be called, for example, addition. Here it is 1 and here it's minus 1. So this is how much the number BV changed. And you can say that BV plus equals add during this operation. Okay, so we have two things, C and BV. We can already check that BV is not 0. Because if BV is 0, then it's impossible to form a path. So we have already two features. And we have already this condition to check. But is it enough? This is not enough to check. Because if we only check this condition, sometimes it will still not be a path. For example, if we have, I don't want to remove it. For example, if we only have some two not adjacent vertices, then they don't form a path, but BV is 2, so BV is nice. We need to check something else except this. So for that, I added a special variable called BB. BB is simply the number of black vertices. BB is the number of, not black vertices, but edges with both black endpoints. For example, in this picture, yeah, where there are these 6 black vertices. Yeah, but there is also this white vertex. Then there are 4 black edges. So BV will be equal to 6, but BB equals 4. So I also want to maintain this value. Why is that? Because I will check that BB is BV minus 1. Yeah, in any path, it should be true that BB equals BV minus 1. Okay, how to check it? How to check it? How to maintain it? So when you toggle a vertex, I will now assume that we turn a white vertex into black vertex. So add equals 1. Let's assume now for now that add equals 1. So we have a vertex. What happens to BB? There are 2 ways BB can change. First of all, let's assume that our tree is rooted, so we chose some root and rooted this tree. So we have a parent this way. So first possible thing is that this edge became a BB edge. And the second thing is these edges became BB edges. So let's start with the upper one. Upper one is easy. We just need to look in our parent, check if it is black, and if it is black, then we need to say that BB plus equals add. So if parent is black. What about here? So here also for each black vertex, here we need to add it to BB. So BB plus equals add times number of our black children. The problem is that we cannot calculate the number of black children in O of 1 time, in constant time, because we just don't know it. There might be many children and we might have to spend a lot of time on checking all of them. So for now this doesn't work well because this set of features is slow. Instead of that, we can add one more array, which is called, for example, black children, BC. BC for each vertex says how many black children it has. So now, so if this is vertex V, we can simply say here add times BC of V. The problem is that now we need to calculate BC somehow. But this is not hard. Let's again look at some vertex V. If it is toggled, how can it change some BCs? It can only change the BC of its parent. So we say that BC of parent of V plus equals add. This is how we maintain the BCs. So we can maintain BC, we can maintain this and this and this. Great. So now we can check that BV is not 0 and BB is equal to BV minus 1. Actually, if BV is 0, then BV minus 1 is negative, but this cannot be negative. So actually, we can now remove the first invariant because it follows from the second one. Unfortunately, this equality is still not enough because sometimes you can have some black vertices, this thing holds, but still it is not a path. This is because actually it can be any tree. In any tree, the number of vertices is one more than the number of edges. You cannot do anything with it. But what can we do? Actually, in any tree, the number of in any like tree, there are many leaves. And only in a path, the number of leaves equals 1 or 2. So actually, it is a criterion. So a tree is a path if and only if the number of leaves it has is at most 2. So we would like to somehow understand if we have a path or not. Well, what I did during the contest was incorrect. I only calculated the lower leaves. That is, the leaves except possibly the root leaf. So in any tree there is a root, and sometimes the root has the degree 1. In this case, it is usually not called a leaf, but in the theorem that I mentioned about the tree being a path if and only if it has exactly 2 leaves, the root leaf should be counted as a leaf. For now, let's pretend that this never happens, and we can only have such leaves. How do we calculate them? I added one more variable, which is called black vertices without black children. This is also of size. This is not of size n. This is just a variable which calculates the number of such things. How can we update it? Again, let's assume that we toggle some vertex v. Which vertices can become or stop being a black vertex without a black children? First of all, this vertex itself can become a black vertex without black children if it does not have any children, black children, and it is becoming black or stop becoming black. So we can say that BVWBC plus equals add, but if it does not have any black children, so if BC of V is 0, so first of all, this vertex can become or stop being a black vertex without black children. Also, for its parent, something might happen. So BVWBC of this parent, of its parent, minus equals add. If P of V is black, so again, for example, let's assume that we have a white vertex and it became black and it has a parent. So the parent sometimes should be stopped, counted here. When should we stop counting it? If this parent is black and it had 0 black children. So PC of P of V is 0, not counting V. Okay? So now we can also calculate this, and actually we can check that BVWBC is at most 2. This is also in a condition which should hold. Okay? Actually, this 2 is almost enough. The only problem is that here we also want to add a root leaf, if there is one. Because in this situation, for example, it is not a path, but everything holds. First of all, it is a tree, so this holds. And secondly, there are only 2 vertices without black children, so this holds. Fortunately, we didn't notice that this is also a bad vertex, and we need to somehow deal with it. So I was thinking about this vertex, so because it has a degree 3 and we can somehow track it, but it was hard for me. I found another way to do it. So I found the distance between these two vertices. Yeah, first of all, I need to know these vertices. In order to do that, I actually need to, instead of having an int here, have here a set of ints which stores the numbers of these vertices. So I just store all vertices which are black and which do not have a black child. When I store all such vertices, I can actually check if there are two of them, I can find both these numbers. I also can find the distance between them. Actually, so instead of finding the distance between them, I can also find the distance via binary jumps, but this is not what I did. Also, I stored a multi-set of all heights of vertices. So for example, if this is 1, 2, 3, 3, 4, then I store and these numbers are depths in our tree. Then I just store this multi-set of numbers. Then I expect the LCA of these two numbers, of these two vertices, be the minimum in my multiset. So I take h of A, where A is this vertex, plus h of B, where B is this vertex, minus 2 times h of, minus 2 times minimum in my multiset, which can be found in O of 1 time. In any multiset you can find the minimum. And this is expected distance. And for example, I can compare it with BV minus 1, which should be the number of edges. So if the number of edges is the expected distance between A and B, then this is a path, because actually you cannot have this thing if you have a path. And you cannot have this thing if this equality holds. Probably in the editorial something else is done. Let's see. Problem E. Solution. Ah, they do this. Okay, I don't like what they did. They actually kept track that no such vertex exists, but for me it was kind of gross. For me it was kind of gross. Yeah, so I did not do that. Okay, I think I have explained enough on this problem, and we can go to problem G, which I solved. I also did not solve problem F, so I don't know what to say to you about problem F. We can look into the editorial, probably. Let's look into the editorial. Consider enumerating each number from 0 to n minus 1, whether it is contained by S. When we have enumerated the first x numbers, there are only 2 to the power n minus x constraints. What does it mean to enumerate a number? Enumerate a number. Yeah, it makes sense, but It's gross. What? This is aqua. E was gross. No, 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 no. I did not like E. But okay. Also problem G. Ah. I don't understand anything about their enumeration thing. Sorry. Ah. Ah, it's so stupid. Yeah, it's just so stupid. Yeah, it's probably very stupid. So what do they say? They say that actually. So we have S. So S is the set in question. So I thought of an ingenious solution to this problem in 2 to the power 2n time, which is the following. Iterate over all possible S, and then for each S that you're trying, take all possible T's, take all T's, yes. Not all T's, but yeah. Can I solve this problem now or not? I'm so scared. Can I absolve it? No, I cannot. So we go through all T's, through all V's. So through all T's in 2 to the power n, and we check that is it true that S intersecting with T lies in the set V f of t. So we just make all these checks. Each check spends this much time. Yeah. So the size of this set can be found with built-in pop count. This thing can be also checked in O of 1 time with masks. So you spend this much time. Okay. But this is too slow. Actually, you don't need to iterate over all possible S. Like stupidly. Instead, we can make a somewhat recursive approach. So let's ask the first question. Does it contains 0 or it does not contain 0? So if it contains 0, we can forget about, or easier n-1, for example. Let's from beginning to end go. Let's go from beginning to end, I think. So does it contain n-1 or does not? So assume that we know it. That we know if S contains n-1. Then actually all constraints of form T, which does not contain n-1, and T, which contains n-1, they can be merged. Because actually, if you know S intersect T, then you actually know S intersect this thing. Because you know whether S contains this element. So you can just merge these two constraints. And now you have 2 to the power n-1 constraints here and 2 to the power n-1 constraints here. Then you can continue. And now you have 4 vertices in our brute force tree. You have 4 vertices in our brute force tree. But this time in each vertex you only have 2 to the power n-2 constraints, etc. So the total complexity will be n times the complexity of each level. Yeah, there are n levels, and on each level there are total complexity of 2 to the power n. So this is the total complexity of your solution. I can even write this because it's not gross. Actually, it's not gross. Actually, it's kind of nice. Unfortunately, I'm not sure that the contest will be tested when it's done, so I will write a solution in the end. And before that, I will explain you problem G. So problem G, as far as I understand, I thought of the author's solution, but not the best constant probably in my solution. So what is the problem? You have 2 strings, S and T. And each of them consists of stars, minuses, and Latin letters. You need to check whether it's possible to replace each minus with a letter and each star with some substring. And the substrings and letters might be different for different minuses and stars, such that S after substitution becomes T after substitution. So can you make S and T equal by replacing some stars with some strings and some minuses with some characters? Okay, the first thing that you might try is to take the last 2 symbols. Okay? If they're both Latin letters, A and A for example, then actually you can remove both of them. You can remove both of them because just you can replace if and only if you can replace after removing both a's. Actually, the same holds if one of them is minus and the other one is either a Greek, either a Latin letter or a minus, because you can, it's always just one symbol, you can always make them equal, so you can remove them. A special case is if these two letters are different. For example, here we have A and here we have B. In this case, the answer is impossible. So when last letters of both elements, of both strings are not stars, you can remove them and possibly immediately return false. So at some moment you stop, and this means that at least one of these two letters is, one of these two symbols is star. Then you can do the same from the left side, and again, you have one of these two things a star. Okay. Also, it's possible that some of the strings became empty. Now let's consider all these corner cases. First of all, if S is empty, it's usually denoted as epsilon. So if S is an empty string, then T should be consisting only of stars. Maybe T is also empty, but if it's not empty, only stars can be there. Because if there is at least one symbol or minus in T, it means that T will never be equal to S. The same way, if T is epsilon, then S should be consisting only of stars. Okay, that's it. Now we can assume that both strings are not empty. Then, at the end of one of the strings there is a star, and at the beginning of one of the strings there is a star. If these stars are in different strings, for example like this, then you can always replace somehow minuses and stars in this string, and then say that this star is whatever is here. The same way you can replace here all stars and minuses with whatever you want, and you say that this star is replaced with this string. After that, S will definitely be equal to T, and the answer is yes. So, if S0 is star T minus 1 is star, then yes. Similarly, if T0 is star and S minus 1 is star, then also yes. Okay, now we know that one of the strings starts with a star and one of the strings ends with a star. And these two strings cannot be same, so they cannot be different, so they are the same. So actually one of the strings starts and ends with a star, and the other string does not. But then we can assume that T contains at least one star, and actually this is also enough for us to win. The proof is simple. You make any substitution here and say that this is your string star. Here you also make any substitution and say that this is your star. And finally, here you make any substitution and this is your value of star. So this is also yes. So if one of the strings starts and ends with a star, and the other string contains a star, then the answer is yes. So we are only left with a case when S starts, ends, and maybe contains some stars, and T does not contain any stars. Actually, you can assume that in S there are no two adjacent stars, because if there are, you can just replace them with one star. Therefore, we have several stars, and between each pair of them there is a non-empty string. Notice that actually these strings should be found in T, and moreover in the same order as in S. So you should be able to find some substrings of T B1, B2, etc., Bk in same order as they appear in S, as A1, A2, etc., AK, and they should be equal in the same order. So this is necessary condition for T to be reached from S. Actually, this is also the sufficient condition, because you can always replace this star with this substring, this star with this substring, etc. So now the question is, you have a string T, probably with minuses, which are treated as any symbol. And you have a string S. Actually, you have now not string S, but several strings. You have several strings. And you need to find the occurrences of these strings in T. This is our task. Find occurrences of some strings in some bigger string in the same order. Or a report that this is impossible. So first of all, algorithm that I learned from Denis Mustafin. So how to do it? How not to do it, but how to resolve some simpler problem. So the simpler problem is you have a string T and you have a string S. Both of them have regular characters like Latin alphabet characters, and they have some not regular characters like minuses. Minus means that you can put here any one symbol. In both S and T, then they may appear. You should find all occurrences of S and T. So you should find all ways to put S as a substring of T such that there is a correspondence. And between any two corresponding letters, they are either equal or one of them is minus, or two of them are minuses. This is also called pattern matching. So you are given a pattern S, you should find all occurrences of it in a source text T, where we say that a pattern matches a string if their lengths are equal, and for any two pair of corresponding characters, they can be made equal if you replace minuses with some characters. Okay. How to do it? It can be done via FFT. Let's assign. Okay, first of all, let's imagine that we have no. Imagine that there are no minuses in T. So minuses are only in S. Actually, let's imagine that there are also no minuses in S. It will be easier. So imagine no minuses in T, no minuses in S. So just the regular strings. Actually, this means that you can solve this problem via Z function, but we will solve it with FFT. Now, for each character, let's give to it some root of unity. Not even a root of unity, but just some number with modulus 1. Let me think how to call. Let's call them P, for example. P0, P is P1, etc. Z is P25. The only thing that we're interested in is that PIs are all complex. PIs are all complex numbers, and their absolute values are equal to 1. What does it mean for a complex number to have an absolute value equal to 1? There is something known as, so if you have pi equals x plus, actually I is not good in this case, j, let's call them j. So it's x plus yi, then there is something called conjugate, which is x minus yi. And when you multiply any complex number by its conjugate, you always get the square of the modulus of this number, which is x squared plus y squared. So you can just check that this is 1. The simplest way to generate a number of which the absolute value is 1 is to generate some angle and take pj equals e to the power I times this angle, which is simply cosine alpha plus I times sine alpha. In our case, we will just take these angles evenly spaced, that is, pj will be equal to e to the power 2pj over 26 times I. So this is our formula. Of course, we will calculate it via this formula, because in C++ I'm not sure that you can take an exponent of an x complex number, but nevertheless. Oh my god, it's testing. Okay, so we have a pause because I want to make sure that I don't get system tests failed. Oh my god, what is it? It is already saying that I spent too much time. Why is it doing it? It's so scary, so scary. Oh no. What? Formless failed system tests? Don't you dare say it to me. What are these shenanigans? Shit. Did he really do it? Oh my god. I don't know. Why would he get wrong answer on a pre-test? This is pre-test, isn't it? It's a pre-test. And why do I see this number? It's strange to see it. "48 milliseconds, guys." Fine, let's go on. So, first things first, we assign a complex number with unit radius to each Latin alphabet letter. I did it this way, but this is actually not really necessary. I'll explain later what is necessary. I will explain later why you want them evenly spaced. After that, we replace each Latin letter with, so in S, we replace each Latin letter with conjugate of it, or of its complex number. So for example, it will be, e to the power 2p I times 0 over 26. Here we'll have e to the power 2pi minus 1 over 26. Here we have e to the power 2pi minus 2 over 26, etc. And in t, we will replace each letter with not conjugate, with regular. So a is replaced with e to the power 2pi times 0 over 26. C is replaced with e to the power 2pi times 2 over 26, etc. Okay, after that, let's find a convolution of array S and array T. Not convolution, but sliding inner products. So when you have two arrays, S and T, there is an operation called sliding inner products. And what does it store? It stores T minus S plus 1 elements of the following kind. Here, we store the sum of such products. Here, we store the sum of such products. Then here, we store the sum of such products. Etc. This can be easily done with FFT. To do that, you need to reverse the array S and multiply polynomial T times reverse S. You just multiply these two polynomials and you get this sliding inner product thing. Okay, after that, let's assume that there is some occurrence of S int T. Then the corresponding element of the inner product will be actually size of S. Why is that? Because for each pair of corresponding elements, since they were equal letters, the numbers corresponding to them in S, it was some conjugate of a number, and in T, it was just a number. So the product was the product of a number and its conjugate, which is simply the square of the modulus, which is 1. So it will be the sum of many ones, which is modulus S. However, if some letters are different, for example, it's C here and D here, then we would have Cj and here we would have Ck. So Pj times Pk. And it will be not 1. Actually, it is never 1 when Pk is not equal to Pj. Because of that, it's still the modulus of this number. It's still 1. Yeah, so if you draw it on a complex plane, it is somewhere on the unit circle. However, it is not here. It is somewhere else. For example, here. Because of that, its real part is less than 1. So each time that you have two symbols which are equal, you get just exactly 1. And each time that they are different, you get some number in which the real part is less than 1. So you will get exactly S if and only if all symbols were equal. If at least once you will have different symbols, instead of S, you will get some number, which either by modulus or by real part, but will be less than 1. And you can compare this number with S and understand. Now there is a problem. If you do it in complex numbers, actually you cannot be sure that the number is equal to S or less than S, because there is something called arithmetic error, and if you're working with doubles or something like that, you can get them. But the question is it true? Then when you added some numbers which are either ones or something with real part less than 1, that you got exactly S. How to understand that? To do that, you need to understand what is the minimum. So assume that you have an addend which is not 1. Then what is the maximum possible real part of this number? For example, if it is 1 minus 10 to the power minus 9, then probably you will not be able to distinguish between this one and this one, because they are really too similar. And after adding them a lot, probably this error will be just lost. How to compare between this and this? To do that, you need to understand actually this maximum real part. And if you have evenly spaced numbers like I explained here, then actually it would be nice, because this means that you cannot get, so maximum real part will be just the real part of e to the power 2 pi over 26, which is just cosine of 2p over 26. So you're interested in 1 minus this cosine, which is known to be let me think. It's a known formula, but I just I think it's 2 times sine squared of p over 26. Sorry if I'm mistaken, but I think it's like this. So for small angles, sine of a number is nearly equal to this number. So this is something like 2 times p over 26 squared. And this is something like 2 times like 0.12 squared, I think, which is something like 0.3. So it is some approximate calculations, but you can easily understand that. No. 0.03, of course. So as you can see, the minimum possible error is 300. So if you all have all ones, then the answer, for example, let's assume that the length of string s is 1000. So you either have exactly 1000 or less than 999.97. Actually, it's really easy to distinguish, because the error of 300 is really large. So for example, what I did in my solution is I compared S with the answer dot real part, and I checked that the difference is less than 10 to the minus 2. It's definitely, so 10 to the minus 2 is definitely bigger than any arithmetic error. So if you get so big error, it's definitely due to one of these numbers being not here, but here. Great. So after you've done this pattern matching, you just iterate over all elements. You check that they are big enough, so they are equal to modulus S, and you know all the occurrences. Now let's make our problem harder. What about S and T having a minus or minuses? Let's start with S. So assume that S has some minuses. Then it's kind of easier. Let's just replace them with zeros. So if we have some symbol, we replace it with complex exponent with number with absolute value 1. But if we have a minus, we just replace it with 0. The motivation is kinda understandable. So when you match these two arrays, you are not interested in what is here. You're not interested in this number. It can be anything. And you are okay with it being 0. So let's just do it. But after that, you shouldn't be expecting the inner product to be equal to S, because there are several zeros. Actually, instead of modulus S, you should expect it to be equal to the number of zeros. Modulus S minus the number of zeros in S. Okay? So again, if you have a minus in S and some letter in T, they just give 0. And if it's not minus in S, then you expect that in T there is a normal symbol. And this means that they should in product give exactly 1 and not some other number with unit modulus. So the same as in the previous case, you just check that you have this number, or at least this number minus 1000 or 100. So like this. Finally, let's consider the case when you can have both minus in S and minus in T. As usual, you expect it to be S minus the number of pairs of symbol in S and symbol in T, such that one of them is minus. So how to calculate the number of such pairs? Actually, this number of pairs is simply minus in S, but not in T. So in T it should be just a regular character, a regular letter, plus the number of places where it is symbol in S, but minus in T, and plus the number of places where it is both minus in S and minus in T. However, in this form, it is not convenient to calculate. Because of that, we will rewrite it as this. The number of places where it is minus in S, plus the number of places where it is minus in T, and minus the number of places where it is minus in both. It is something that you usually do in exclusion-inclusion principle. Okay, how to calculate all three things? So how you're making a pattern matching. So you have some string s, you have a bigger string t, you somehow aligned s with a substring of t, and you're interested in three things: the number of minuses here, the number of minuses here, and the number of minuses in both positions simultaneously. Okay, the first thing is just the number of minuses in S, which is a constant. It can be calculated in previously. Recalculated, as we usually say. This is just number of minuses in S. Okay, what is number of minuses in T? Unfortunately, I got via 31 or something like this because I just similar way calculated all numbers, all minuses in T. This was not correct because you only need minuses in this area. To do it properly, you need to fastly understand the number of minuses in a substring of T. And it can be done with prefix sums. So for each prefix, you calculate the number of minuses in this prefix with a simple for cycle. And then when you need to calculate the number of minuses in a substring, you need to subtract this number of minuses and this number of minuses. So from this number, you subtract this number. And this is what you're left with. So this is prefix right position minus prefix left position. Finally, number of minuses in S, which are simultaneously number of minuses in T. So this is a problem of the following kind. You have a binary array S, you have a binary array T. You consider all alignments of S with some substring of T. And you need to find in each of these alignments the number of ones which are in the same time ones in the other array. And this is done with another FFT, but this time just an integer FFT. You reverse S, you multiply the polynomial S reversed and T, and the coefficient in the product is just the number of ones which are both in S and T. So this is coefficient of product of minus polynomials of S reversed and T. So this is how it is done. Okay, let me recap what I was talking about. We had a problem given a string T and many strings S. Check if it is possible to find substrings of T in the same order which correspond to these substrings S. And before explaining this problem, I explained a simpler problem when you just need to find all occurrences of one string with pattern symbols like minus with gaps into another string with gaps. Okay. How to solve this problem, which I'm... if I didn't say that, the complexity is O of log n, n log n, where n is just the size of string T. Good. So what do we do here? Actually, the first solution is straightforward. Let's take the first string S and find its leftmost occurrence in T. It can be done in T log T time. Okay, if the size of S total is n and size of m T is m, then you can do it in m log m time. And there are case strings here. Okay, then we take the second string and we do the same thing, but greedily after the first string has ended. So we do it here. We also find the second occurrence. We also cut the string t, and the third one is searched after this place. In total, we will have to spend k m log m time, where m is the length of t and k is the number of strings in S, in the array S. This is slow because k can be big, m might be big, and you have the slow solution. In order to fix that, additionally to we will have to make some optimization. This is a common thing in FFT based solutions. So what we would like to do is to do it in O of S time. Yeah, so you would like to do it in O of S time. Because this way you would actually, so these numbers would add up, and in total you would have kn log m time and not kn log m log n. So instead of that, you would have sum of si log m, but this sum of si is not kn, but just n. So it would be n log m. The problem is that since, for example, if you have this string s1, it can first appear somewhere here. And to understand that, you need firstly to go through all these symbols. So you cannot do it in O of S time. Okay? What can be done is the following thing. So assume that you have a string t, you have string s1, and you're searching for s1 in t. It is stupid to spend t log t time to find s1 here, because s1 can be really tiny string, and you can find it really near the beginning. So you didn't need to process all these numbers here just to find something here. In order to do that, let's, instead of looking through all elements of t, take first s1 times 2, for example, elements. So you just consider these many elements. And you only search for s1 here. In this case, you spend s1 times 2 time times log s1 times 2. This is how much time you spend. What do you get? You either understand that you have s1 here and you find it, okay? Or you understand that it is not here. Probably it's somewhere here or maybe here. But you definitely can say that the first s1 characters here are not needed. So if any character of this string s1 was intersecting with this area, then actually all this string would be inside this s1 times 2 thing, and you would win. It is not the case. And actually you can ban all these symbols. After that, you can continue starting from this point. Okay? So actually, each time you fail, you kill s1 elements of string t. And each time you succeed, you also spend this much time, but you come to next string si. So complexity equals total time on successes plus total time on failures. Okay, each time we have a success, we just have this thing on different string of t. So this is in total something like si log si summed up, which is just n log n in worst case. Okay, what is the total time on failures? Each time you have a failure, you spend b log b time, where b is the number of banned symbols in t. And you cannot ban the same symbol twice. So in total, you will ban each symbol of t at most once. So in total, you will spend at most t log t time. So this in total is at most m log m. And this can be rewritten as m log m simply because m is at least n. If m is less than m, then you simply cannot have all occurrences of s and t. Oh, that's basically it. Unfortunately, what is used here, so I'm not sure that you really need to put 2 here. For example, I wrote 2 here and got TL. For example, maybe 3 is better, because 3 did not TL. I can also try writing some other constants. Let me try, for example, submit. And I will put, for example, 4 here. Maybe 4 is even better. 4, 5, 6. Let's do it up to 10 and see what happens. Hope that happens is not that Mike's comes to me and bans. 8. 9. And 10. Actually, it's too big numbers. Let's also try something like 1.5. Or maybe 2.5. And maybe 3.5. As you see, it's very numerically unstable, and maybe I'm even too lucky to not have any problem. Yeah, my solution is not really stable in terms of time limit. Okay, we'll take that. What can I say? What can I say? Okay, problem F. Last thing that I would like to do is to try and solve problem F. So, what do we have in problem F? We have just n and then a lot of numbers. A lot of numbers. A lot of integers. Actually, I don't need n because I can calculate n via v. Viance equals find ans of v. And for int I commands count I. Okay, find ans is vi. Great. Let me think. So what? Let's say that we will make some recursive procedure which will fill the answer into an array ans, which will be returned in the end. Okay. We also will have so what do? We will have function void which returns void. Of what does it do? It takes as argument the vector of constraints, actually. Great. So we have a recursive function which takes the vector of constraints and returns nothing. But it just pushes the answer into the void. Also, let's kind of give it the current mask, which is already processed. Great. So first of all, we need to understand. So now, then we say rec of v and 0, and we return answer. We need to consider two cases if we take some element or not. Let's firstly understand which element. So how many constraints are there? So let's say that we have constraints dot size. Okay, let's then take leading zeros. And actually the number of leading zeros is simply the number of elements that we have. So this number of elements that we have. So we can check if we want to take n minus first element or not. Okay, so let's say that we create the vector of constraints of size n minus 1 and let's go through it. So in the set J, there is no such element. Yeah, so we just take this thing. Also, in the set J plus two to the power n minus 1, okay? So in this set, there is this element. So depending on I, we will also have it here. So in this case, when we remove it, we need to move it to I like this. I think, yeah. Okay, then we say that we run a recursive function for a new constraints and mask or delete number. Why? Ah, so I need to say this. Yes. Like this, I also think. Great, that's it, I think. Ah, we also need to print the number of possible numbers. Let's do it. Of course, it failed. There are several reasons. First of all, what? First of all, actually, we never leave our recursion, so it is infinite, unfortunately. N is big. Why? Ah, count trading zeros, yeah. So my recursion is still infinite, so it will definitely fail. Yeah, but it failed for other reason. Because here we should have a question about zero. So if n equals 0, then we need to say that so if constraints dot front contains 1, only then we ans dot pushback mask, and else we return. This will not work because actually for it to work we need to replace v0 with some big number. So how to do it? We say this and we say this. And we say this, yeah. Now it should work, I think. Now there are no reasons for it not to work. Yeah. 3, 5, 6, 7, 119. Can I submit now? Yeah, I can. Well, it's a nice problem. I am kind of sad that I did not solve it. But this is because I was not able to. Well, the video is already too long, so thank you for watching. Please participate in contests. Ours is 100th place. Yeah. Good luck.